the way it went. If you've got the signed area under some curve, and if you can somehow find the antiderivative for the function, and the function meets all the requirements, continues, or more or less well behaved, you can just evaluate the area by finding the antiderivative, evaluate at B, find the antiderivative, evaluate at A, and subtract them. As easy as it sounds, that's all it took. And that changed everything. That changed the game forever. Your mind was expanded and it can never be contracted from that point on. But interestingly, now that takes us into a different direction, because now all of a sudden antiderivatives become of the utmost importance. Being able to find antiderivative for any given function. If I've got some function here, it becomes incredibly important that I can find the antiderivative of that function. Find a function whose derivative is exactly this. It becomes so important that we change the sign a little bit. The sign the symbol takes on a life of its own. We abandon these limits. Say, you know what? Forget about those limits. We will worry about those later. At the moment, we simply want to focus on finding the antiderivative. And so, rather than having this symbol here, we make up a new symbol with no limits. And this one just represents the antiderivative. The antiderivative of f of x, and there might be more than one, and so in fact there's always more than one. So we add a little word here, the general antiderivative of f of x, and that's a whole new symbol. It's called or the fancy name for it is it's called an indefinite integral. And this will be the name of the game for the next week or so. We will do nothing but find antiderivatives. We will do nothing but calculate indefinite integrals. Those two statements are saying the same thing. And we won't worry about these limits so much as we did over here. That's called a definite integral. We'll leave those alone for a second and focus on the real heart of the problem, is finding the antiderivatives. Evaluating these endpoints, that's cake. That's really easy. Finding the antiderivatives is a whole different story. Okay, so we focus on these antiderivatives. We can go in pieces. We'll go in departments. We can try, for example, first the easiest ones, which would be the power rules. This would be the analogous of the power rule for derivatives. If you remember, when we had the when we were doing derivatives, the first part of the course, we said, hey, what's the derivative of x to the third? And we say, well, that would be 3x squared dx. Yeah. What we now have to do is we have to undo this using antiderivatives. So now we would say, let's go with yellow now. Today we would say, what's the antiderivative of 3x squared dx? And the answer would be, I'm looking for a function such that when I take the derivative I get this, and that would be x to the third. But actually x to the third is not the only one that works. X to the third plus 3 also works, but x to the third plus 4 also works, but x to the third plus 7 also works, because when you take the derivative of every one of these, you still get that. And so what we mean by the general one is we say, well, x to the third plus some constant c. Any form like this, any function that has this form, x to the third plus 3, when you take the differential of it, you will get exactly this expression. And so this would be the opposite of the power rule. What we want to do is practice the power rule a lot, or the antiderivative, the anti-power rule, maybe would be a good way to call it. And that's what we're going to do. The next few examples we'll just practice this. But let's practice the power rule, the anti-power rule. The anti-power rule goes like this: if this is x to the 5, to have to take the derivative and get x to the 5, you must have had x to the 6 before, so that when you bring it down, you subtract 1 from 6 and get 5. In addition to that, because there's no coefficient here, that must have been killed. So what you do is you divide by the new 6, so that when you bring it down, it kills the 6 and you have no coefficient. Again, let me do that again. All you do is you add 1 to the exponent, and then you divide by the new exponent. And what that does in effect is it prepares it so that if you were to take the derivative and check it, you would bring the 6 down, cancel that, and you subtract 1 and get the 5. This is exactly the undoing of the power rule. And that's how you do it. All these ones with that are just polynomials or some version of x to some constant power. That's all you got to do. Want to see it again? Let's do it again. If you have x to the 7th, what you would do is you add 1 to it, x to the 8, and then divide by the new 8, and then do a constant. See that? X to the negative 5. It doesn't matter if the exponent is negative, as long as it's a constant, just a plain constant. You can play this game all day long. You do negative 5, you add 1 to it, that would give you negative 4, and you divide by the new one, and you add a c. And it's easy to check here. We'll do a little check here. Let's do the check in red. So this would be a little check. On every one of these, you can easily do a check. You do the differential of x to the negative 4 all over negative 4 plus c. Well, that would be the differential of the product. So you do the sum. So you could do this negative 4 over negative 4 plus a differential of the constant. This part goes to 0, so forget about that one. That goes to 0. This one would be, you bring it down, that would be negative 4x, and then you subtract 1, that would be negative 5 all over negative 4. This would cancel, and then you have a dx by using the chain rule. You bring it down, subtract 1, the differential of the stuff, so that would give you a grand total of x to the negative 5 dx, which indeed matches what we started off with. You can always do a little check on these to see if you did it right, just by taking the derivative. Okay, let's do it again. Again, I want to emphasize that it doesn't matter what it is. If it's a constant, you just add 1 to it and divide by the new exponent. If that exponent is a constant. And also the letters, it shouldn't matter if it's x's or t's or u's, whatever. As long as this matches that, you can play this power rule game. So it would be u, and it would be 2/3 plus 1. That would give you 5/3, and then you divide by the new exponent, 5/3 plus a constant. And then you're done. See it? That makes this stuff look easy, huh? Even if there's a constant there, don't even worry about it. Those constants can come right through the integral sign. It's one of the famous properties. And so you don't even worry about the 7. You could worry about it later. Just keep the 7 out there. Just worry about the integral here. The integral would be t, you add 1 to it, 7/3, you add 1 to it, that would give you 10/3. And you divide by the new exponent, 10/3 plus a constant. So that would give you a grand total of, you could flip this one, that would be 21 over 10, t to the 10 over 3 plus c. And it'd be really easy to check this by taking a derivative and making sure that you get that. Okay, it's called the power rule. Again, I want to emphasize, it doesn't matter if you've got constants, they can come out. And it doesn't matter if you've got different variables, as long as these match. And it doesn't matter what constant you have as an exponent, as long as that exponent is a constant, you can use the power rule, the opposite of the power rule, which would mean you add 1 to the exponent, that would give you pi plus 1, and then you divide by the new exponent, that would give you pi plus 1, and then you add a constant. And you don't even have to distribute this 5/12 times the constant, because it's just a constant. So if I multiply by 5/12, it's still a constant, so it'll absorb it. It'll just be a different constant, but there's no point. You can call it whatever you want. There's no point in changing that. And so the grand total you could write is 5/12 all over pi plus 1 times w to the pi plus 1 plus a constant. That would be acceptable. Okay? All these are just examples of the power rule. This is an interesting one. There's nothing here. When there's nothing there, you could do it two different ways. You can imagine. I'll do it two different ways. Okay. One way to do it is you can imagine that there's a 1 there. By multiplicative identity, 1 times dx is the same thing as a dx. And then you can start to think, all right, I need a function f of x, which is equal to I don't know what, so that the derivative of it, f of x, is equal to 1. Which function is there such that when you take the derivative, actually 1 dx? Well, that would be x. X would work there, and so you could just say x plus c. Here, you could check. Let's check real quickly for fun. What's the differential of x plus c? Well, the differential of x plus the differential of c would look something like this. This would go to 0, and that would just be a dx, and this matches exactly what you have there. So the integral of the derivative of x is equal to just x plus a constant. But this is more interesting than that, because it actually, let me see if I can clone this page and try the same problem, but this time I'm going to try it a different way. I'll erase everything. this time I'm going to try a different point of view. Here's a different point of view. You can think about it this way. The integral is the antiderivative, and this is the derivative. They will undo each other and just give you x plus a constant. That's a really interesting and powerful way to look at it, because if you had something like d integral of du, well, you think, hey, these two undo each other, and all you get is u plus c. But that's not why it's interesting. It's interesting because you can have any stuff here. The differential of star. Again, these will just cancel each other, but that's not really why it's interesting. Here, I'll show you now why it's interesting. The differential of e to the x. On the one hand, you could say, well, that would be the integral of e to the x dx. But on the other hand, you could say, well, they do undo each other. It's just e to the x plus c. And you could have any sort of stuff in there. The antiderivative of the derivative of any stuff would be the stuff plus a constant. That's what's interesting about it. Okay? Again, you could have anything. The antiderivative of the derivative would just give you the thing itself. They undo each other. You could have anything. Antiderivative of derivative of star, that would be star plus a constant. And what kind of star is that? That would give you star plus a constant. It's a little better star. Okay. Also, if you have pieces together, sums or differences, that was one of the famous properties. The integral of the sum would be the sum of the integrals. So you would say, you know what? Don't even worry about it. I could do this. I could break this up into little pieces. I could do 3x to the 5, and this dx gets distributed. Plus 4 integral of x to the 7th dx plus 6 integral of just dx. That's what happens when you distribute the integral to each one and the dx into each one. And so all you have now is a bunch of little smaller problems, the kind that we've done already. So this would be 3 times x to the 6 over 6 plus, and I don't have to add a constant here. I can just add one constant for all of them because there's so many of them. A constant plus another constant plus another constant will still be a constant, so I'll just add it at the end. It will absorb all of these. Add 1 divided by the new one. 6, these do undo each other, x, and then I'll just have one big constant for all of them. Okay, that's how you do sums or differences of a bunch of functions. Clear? Pretty easy, right? There's only one exception to this power rule, and that's this exception, because, let me explain why. If you have u to the negative 1 du, you might think, well, you know what, I'll just use the power rule because that looks like a variable raised to a constant. So we said, hey, anytime that happens, you can use power rule. Then you go on and use the power rule. You add 1 to it, that would give you 0, and then you divide by the new exponent, and you say, whoa, 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 whoa. Timeout, violation here. This is not good. So this is the only exception to the power rule. Luckily, this is a famous one. This is a famous one. When you have u to the negative 1, this is a famous one. Let me remind you. By the way, this is a good time to introduce. This is super, super important that you're really, really good with the famous derivatives. You had all these functions here, and you took the derivatives, and these were all the derivatives. You had all these famous functions here, and all the famous derivatives. You scan through it, and you see, whoa, right there, look. What happens there? The derivative of ln x is 1 over x. That was without chain rule. With chain rule, it would look like this. ln of x, the differential would be 1 over x dx. And that's exactly what we have here. Alright? Where do we have it? Right here. We have 1 over u du. And so it's the famous one. It's the only exception to the power rule. The way we do this one is, just making it red so that it stands out, is ln u. And to be honest, to be completely correct, it really should be the absolute value, because ln is not really a real number if u is not positive. A lot of times I'll forget to use absolute value, but really you should. And that tells you something also about the limits. If you were to later on add limits on here, these limits better be on the positive side, or you better make sure you put the absolute values on there. Okay? Plus a constant. This is the only exception where the anti-power rule will get you wrong answers. It'll get you dividing by 0, which is not allowed unless you're Euler. Euler, the most interesting mathematician in the universe. They told him not to divide by 0, and he divided by 0 anyways. So this is the only problem, okay? If you want to use the power rule, you're going to be divided by 0. You're going to get into a lot of trouble. Use ln in here. Alright, so I think we should move on to other kinds of antiderivatives. We did a lot of power rules. Really, that just takes care of, let me think. Let me erase this. That just takes care of these two. We learned this, how to undo that. Instead of subtracting, we add 1. Instead of multiplying, we divide. Check. That's what we did right there. We did this one. This one, it just says the differential of x. If you anti-do it, you just get x. That one. We did this one. This is the only exception to the power rule. And we still have a lot more to do. Every one of these statements that has a derivative statement is also an antiderivative statement if you just look at it from right to left instead of from left to right. Let's take a look at some of these trig ones, for example. Yeah? Let's take a look at some of these famous trig ones. You really need to know this. This lecture is a little bit different than other ones because it requires a lot more participation from you. You really need to do the homework. I could do 1,000 of these. That's not as good as you doing 10 of them on your own. You really must take paper and pencil and actually work through the homework. In fact, you should be doing that on all the homework. But it's especially important here because I can't do much of the learning for you on this one. I can only tell you that it's really important that you know all of these things really well. Alright, so let's do this one. The antiderivative of cosine. Oh yeah, this is a trap. This is a trap I said on purpose because this is dx and this is t, and these don't match. Think about originally what that meant. We had some function here. Think about what that meant originally. You had some function here. Suppose this was t and this was f of t. Okay, you got some function and you're trying to find the area or the signed area or whatever. But what happens if you have some function f of t, but you have x-axis dx? That's a totally different axis. Then you know they're not compatible, and so you've got some issues here. You really must make sure that they either match or you can exchange the t's for x's or something, because as it is, this is just a caution example. Make sure these letters match. Okay. Now, if it looks like this, that we can do. Or if it looks like, let me think. If it looks like that one, we can do t's and t's. Alright, let's do this one. Let's do this one, but let's do it the right way. So suppose that I'm going to take this one away. Here's what we really can do. The integral of cosine, let's make them both x's, x dx. That we can handle. So what we got to think about here is we got to look for a function, such that when I take the derivative of it, I get cosine x dx. There's another way to do it. So you got to think, or if you don't like thinking that much, you can look. Just look at your famous sheet here. Is there one where the derivative is cosine? And that would be an affirmative yes, right here. The derivative of sine x is equal to cosine. Right? Here, I'll emphasize it again. The derivative of sine x would be equal to cosine x dx if you were to use chain rule. That tells you exactly how to do this one. So it tells you that what goes here is the sine x. And so this would be equal to, let's go with y, this would be equal to sine x plus a constant. Okay? Let's pause this to answer the phone. But this one, the antiderivative of sine x. At first you might think, well, that's easy, that would be cosine. Sorry, the antiderivative of sine t. That would be cosine t. But then if you check it, you realize that the derivative of cosine is negative sine. So that's not negative sine, it's positive. To cure that, you add an extra negative here, and that takes care of the problem, because then you have the derivative of this thing would be negative sine, but you got another negative that would turn into a positive sign, and you're done. That's it. It's often useful to think about this cosine sine circle. Here it goes. if you have sine x and you were to take the derivative, I knew I should have practiced this before, and you were to take the derivative, that would give you cosine x, right? And if you were to take the derivative again, that would give you negative sine x. And if you were to take the derivative again, that would give you negative cosine x. And if you were to take the derivative of that, that would give you sine. This is the derivatives. If you were to take antiderivatives, you would simply go backwards. You would go backwards for antiderivative. You would go backwards for antiderivatives this way. Okay? So, for example, the antiderivative of cosine x dx, I would just find my cosine here and go the counterclockwise direction. That's equal to sine x dx. The derivative of cosine x is that. The antiderivative, suppose I wanted to find the antiderivative of negative cosine x dx, I would find this spot and go the antiderivative direction. That would give me negative sine x plus a constant. Get it? This way you take derivatives. Clockwise you take derivatives. Counterclockwise you take antiderivatives. The antiderivative of sine, negative cosine. The antiderivative of negative cosine, negative sine. The antiderivative of negative sine, cosine. The antiderivative of cosine, sine. Told you, super famous. Okay? By the way, there's a famous one too for e to the x. Here, e to the x, let's go with yellow, because it's mellow. E to the x, if you take the derivative of e to the x, what do you get? Well, you get e to the x. If you take the derivative of the x again, you get e to the x. Haha. So, the antiderivative would just be so simple. It would just be going backwards. This way you would... This is silly. It's the same thing. Forget it. Anyways, let's go back to trig. We're doing trig once. That one's famous. That one's famous. We did that one. That one. How about this one? Again, it might look complicated. Secant square. But the thing you got to remember is, right now we're just doing the very, very, very basic ones. What that means is that they're probably here on the basic sheet. If they're on the basic sheet, they're basic. Okay? If they're on the famous sheet, they're famous. That's why it says they're famous. So you scan the right side and you say, hey, are there any of them that are secant square? And you say, yeah, there's a function that the derivative of it is secant square. That function is tangent. That's it. That's game over then. So the antiderivative of this would be, stay consistent here. The antiderivative of that would be tangent t plus a constant. Why? Because I just looked at the famous sheet. If I take the derivative of tangent, that's secant square. See how easy that is? You say, whoa, that looks complicated. Secant times tangent. Really, really complicated. But then again, the most important thing about this section is you got to know the famous sheet. There are functions where you take the derivative and you get secant x tangent x. And the answer is yes. Here's one right here. Secant x tangent x. Which function is there such that when you take the derivative you get secant x tangent x? Well, that would be secant x. As soon as you realize that, it's all over. This would be equal to secant u plus a constant. Why? Because the derivative of secant is secant tangent. See? Famous. The famous ones are super easy. All you do is look at the famous sheet. Talked about this one. What's the antiderivative of the x? Well, e to the x plus a constant. It's too easy. Okay?